Hello, Accelerated Math 7-8 students. We are working on Module 12, and this is Lesson 13. Lesson 13 is called First Consequences of Fundamental Theorem of Similarity. So it is completely based on what we were working on in our last lesson. So here we are. We have First Consequences of Fundamental Theorem of Similarity. Our goal for today is today we will try working backwards with the fundamental theorem of similarity to see what we can remember about the fact that if you have the same scale factor, then you should be able to create line segments that are always parallel as long as you use the same scale factor. So what can parallel lines tell you about FTS? Hopefully you can figure out that question from this. And then once you know that, what can you conclude about that? All right, so the center is 0, or O, and there is a segment called OA. The scale factor is 6/4. Where would segment O prime, A prime be? Okay, so we're looking at, and actually I don't even know if we would call this O prime because we're not changing where the O is. The O is actually still there, so it would actually just be OA prime is what we would call that. So our center O that we're talking about, when you're given a center O, it means that your center is at the origin. So that's really, really important because if your center of dilation is not at the origin, then you're going to come up with different results. But because we're at the origin, we need to pay attention to what we learned about FTS, and we figured out that if we take the original, which in this circumstance would be OA, and we multiply it by the scale factor that we were given was 6/4, and that would give us OA prime because that is the new position of the segment. Okay, so if we have OA, here's OA right here, I hope you can see it. The scale factor is 6/4, so we have to take what we know about OA and multiply it by 6/4, and that will give us OA prime. So if we're looking at the graph, which that's what we're working with is the coordinate plane, we can figure out the length of this by remembering our Pythagorean theorem that we've been working on, because we know that when we're working on a graph that all lines are perpendicular to each other based on where you're using it. So if you would do me a favor and just drop a perpendicular line from A, and now you can see that there is a triangle that is presenting itself right here. So if we closed in our triangle like this, we can determine the length of those sides, remembering that this is where your right angle sits because it's perpendicular, and remembering that our hypotenuse is always across from the right angle, so this would be our C. And then does it matter which one is our A or B? And our answer is to that is no. So I'm going to label this one A and this one B. So knowing that, can we determine the length of A and B and C? And the answer is yes, because we're already given those. So what is the length of this segment right here? So you just count your units. So we have 1, 2, 3, 4, 5. So you know that A is 5. Okay, now let's figure out what B is. B is 1, 2 grid lines, so that would be 2. And now we remember our Pythagorean theorem that we have A squared plus B squared equals C squared, correct? So we have A, which is 5 squared, plus B, which is 2 squared, equals C squared, okay? So 5 squared is 25, 2 squared is 4, equals C squared, okay? So that's 29 equals C squared, okay? And then what we're supposed to do to figure out C is take the square root of both. So we have the square root of C squared, and we have the square root of 29. And so we know that C equals, and we talked about this in class, if this is your square root that you're trying to find, we have to find the perfect square below and the perfect square above. Well, I know the perfect square below is 25, and I know the perfect square above is 36. So I know that the square root of 25 is 5, and I know the square root of 36 is 6, and now we find the distance between them. So 36 minus 29 is 7, so there's 7 in between these two, and the distance between these two is only 4. So we're going to say that C is about, remember, 5, okay? And so we would know that if we actually used a calculator, that we would know that it's 5 and a little bit more. So we would say 5 dot 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 dot. Okay, about. So we now know that this is about 5 and something. Okay. Now we have to use that information to figure out what OA would be, or where we would place it. So we're looking at the scale factor that we have right here. Okay. Could you tell me where point A sits? So the coordinates for point A are 5, comma 2. So my question to you is, could we take this ordered pair and multiply it by 6/4? And the answer is yes. So we're going to take 5 over 1 times 6 over 4, right? And that gives us 34ths. Okay, so that's the new point. So we would say 34ths is the first, right? Comma. Now we're going to do the same thing where we take 2 over 1 times 6/4, and we get 12/4, which is actually 3, right? So 34ths is actually 7 and 2/4, which is the same as 7.5. So we would know that this one is actually 7.5, comma 3. So that's where we have to put our new A. So we're going to go to the right, 7.5, and we're going to go up to 3 and look at where we actually end up on the line like we had. So that's perfect, okay? So again, if you were to drop a line here, what do you notice about this line and this line right here? They are parallel, okay? So we proved the FTS right here. We did a little extra work, and the reason why I threw in the extra work is because I wanted it to be a review for you to remember that you can use the Pythagorean Theorem to help you. But ultimately, the question that we were looking at is, what can parallel lines tell you about the FTS? And what you need to answer is, they have the same, what? The same scale factor. That's what it can tell you. So what we can conclude is that if you have parallel lines and they are shared from a given line, right? The line was given and we found the new point and we dropped a line perpendicular to the x-axis, this line and this line will be parallel, okay? You also can remember that any line on a graph, if you drop a perpendicular line to the x-axis or a horizontal line to the y-axis, can create right triangles. And once you have right triangles, you can figure out the lengths of those using the Pythagorean theorem. Okay? So today we will try working backwards with the fundamental theorem of similarity. You're going to have some more problems like this on your practice, and there definitely is one on the test. So you need to pay attention to what we were doing on that. All right, kiddos, that's all I have for you today. Hopefully you're starting to see and understand the fundamental theorem of similarity. These two lines are similar because they are parallel. The only difference is they're different in size. Okay? All right, I'll talk to you soon. Bye.